Hello, everybody. Welcome back to our YouTube channel where you learn everything Kotlin. And today we're going to have a very interesting topic to talk about. And well, if you follow me on Twitter, like that's my Twitter handle right there, I've been asking people what kind of content do they want to hear at our webinars. And there were quite a few folks mentioning coroutines and especially Kotlin Flow. So coincidentally, we have a speaker for this specific topic. Yury, hello.
Anton, thanks for having
Hi.
me.
Yeah, Yury is coming from a very interesting company called Synthesized, and they make a product that transforms the data from like pumping it from one point to the other. And apparently, they applied Kotlin flows for scaling the application. And Yuri is going to, explain how they applied Kotlin flow and what are the benefits of using it, and maybe a little bit about the product as well, because it's quite an interesting tool for the developers, like to simplify our lives. So without further ado, we're gonna start right now. One comment though is that I'm monitoring the chat, so I can interrupt Yuri during the presentation if I find a relevant question. Don't hesitate to post your excitement, cheers for Yuri, and all that. So without further ado, let's start. Yuri, the floor is yours.
Yeah, thank you. And hi all who's currently watching us online. Today we are going to talk about flows, and we will do that using a practical example. Actually, this example stems from the real-world task that Synthesized is currently tackling with one of its products. And let me outline the task first to explain what are the complexities and what are the parts of it that we will be trying to solve, at least trying to approach during our today's session. And of course, we will do that with flows. All right, so the problem we are trying to solve here is, well, in a nutshell, it's very straightforward. We have a set of input databases, one or more, that contain sensitive data. And sensitive is defined very broadly here. It can be data that is subject to certain regulations. It can be business know-hows, like financial data, maybe user data, which is subject to privacy concerns and stuff like that. However, we define this sensitivity term. We cannot allow such data to leak into less protected environments, such as local development environments, or I don't know, staging, or maybe a CI environment as well. We need certain instrumentation applied on top of the production data to make them sort of not sensitive, to remove the sensitivity. But at the same time, we need to preserve the utility of the data, because it's very simple to produce gibberish, right, and fill the output database with it. But it's much more complex to actually preserve the qualities of data that would allow, for example, our services to run on top of the synthetic data and not break. And the simplest example being like emails must remain emails, usernames must rename names, right? Credit cards must also be credit cards in the output. So yeah, and another challenge in this task is to preserve the sort of shape of the data, right? So when we have a relational database, that's not just a disparate set of independent tables. There are different constraints, references between them, foreign keys that impose the parent-child relationships, and we must preserve all of that, right? So this manifold complexity is actually being tackled by the product named Test Data Kit, or TDK abbreviated. And as I described it, even though it sounds kind of straightforward, it's a huge problem. That's why the entire kind of separate product exists to address it. And today we are going to reduce this problem to just a few bits that we will try to use as the basis for our toy solution, which we will develop right in front of your eyes using Kotlin flows. But first, a few words regarding the tool itself. Here I'm talking about the so-called TDK Lite, which is a simple command line-based tool written in Kotlin, of course. It's distributed as a single file, and one of the overarching goals of its design is to use as a little explicit configuration as possible. So as much as possible is being inferred from the input and output database information. And yeah, so that it's just, a very simple, very extremely simple, on the verge of being simplistic. So yeah, this is how TDK Lite operates. And with that in mind, let's understand what we will be doing throughout our today's session. So first of all, we'll take a modestly simple and at the same time quite complex structure of tables, which I'm depicting here. So we have how to call it, a cluster, a clump of tables connected with foreign keys, and one standalone table just as an example of something that can be processed in an embarrassingly parallel mode. We will take this input database, we will run it kind of through our application that we will be developing, and we will create a replica of that database. But it won't be like a one-to-one replica. We will apply so-called masking on top of the data. And what is masking in our case? Well, as I mentioned, we want to get data at the output that resembles the original one, right? So if we have this band of 3 nice young people and we apply masking on top of this data, I mean, particularly this name attribute, we want to get some, names in the output which still look like names, but those are not real persons. Okay, and the masking is is an entire domain in itself. It's kind of entire universe. There are families of very special masking algorithms, namely the family of format preserving encryption algorithms that address exactly this task. But for our purposes, that's kind of immaterial, that's too complex. So we will get away with a simplification, kind of oversimplification, actually. We will do our masking with CSS code. And for those of you who are not aware what CSS code is, it's just taking a string and applying a fixed offset to the string characters so that we get something kind of resembling the original, but already modified. And without knowing the offset, we kind of only can guess what the pre-image was, right? So here, for example, I'm using scissors offset 1, and I transform our brave guys into, I don't know, a band of hobbits, maybe. So yeah, the names completely modified, right? And that will be enough for the purposes of our demonstration because our focus is flows anyway. Yeah, this is a local fiction anyway. But before we jump into the coding exercise, a few words on how we came to flows in the first place. So a while back, when we were scaling our solution from a simple prototype to like a full-blown tool that is capable of handling not toy databases, but quite large databases of gigabytes and tens gigabytes of data, We were thinking about what could we pick actually, right? What we wanted to get was the utilization of multiple cores available to us, ability to process graph structures, meaning that when you model the topology of any database, it can be represented as a graph, right? And we wanted to preserve it. Naturally, we had to deal with data streams. So whenever you read a table and you want to do it efficiently, you have to read it as a stream of records, right? But at the same time, we wanted to preserve this simplicity that was inherent to our solution. So still one file distribution, still minimal configuration. What that meant for us is that it rolled out distributed processing engines, at least for the light mode. We wanted to have as little boilerplate as possible. So we didn't want to have all those concurrency primitives scattered all over our code. And we could not afford complex orchestration frameworks not to bloat our configuration with that. So simply speaking, we were left with just JVM-based concurrency within a single JVM instance. And probably for most of you, that's very well-known set of facilities. Of course, plain old thread pool executors and stuff. Actors maybe reactive streams. But actually, since we already were writing in Kotlin, we wanted to make our solution as Kotlin, kind of leave it as Kotlin friendly as possible. And we were very reluctant to bring any third-party libraries to our solution, both in terms of increased size, but as well, we wanted to keep it as simple as possible in terms of external dependencies. So that's how we turned to Kotlin flows. And the last thing that I want to oh, by the way, is this pop-up about us? Join our webinar. Yeah, it's about us. Anyway, so this is the flows documentation. And at first sight, it didn't look advantageous at all. It's kind of drab, honestly. No fashionable, no kind of posh marble diagrams, lots of plain text, all interactive though. And, seemingly few operations, so not impressive at all. But it's actually, I would say, a blessing in disguise. When you start experimenting with flows, you start noticing that with just a few operations, by smartly composing them, you unlock access to building arbitrarily complex reactive systems. And by scratching the surface of flows today, I hope that we will see how this works. And even though the example will be very basic and we won't dive too deeply into some specifics of flows, I hope to show that the flows are very powerful, and at the same time the learning curve is not that steep as it is for maybe other reactive solutions. All right, so that's it about the intro part, and we're ready to start coding.
Show us the code.
Yep. So I've prepared a few helpers so that we won't get distracted by some irrelevant part. But first of all, let me show you how the database looks like. So we will have a kind of completely contrived example here consisting of 5 tables. And as I promised, one table is completely independent, and the 4 other tables are in parent-child relationship with foreign keys defined on them. So for example, we have departments and projects with department ID referring to the attribute in the parent departments table. So the structure is quite complex because here we have one employee projects table that refers to 2 parent tables at the same time. And we'll see how that unfolds in terms of processing such structures. So here I'm defining a few methods to ease further interaction with databases. So here we have the read method in the DB wrapper, which returns a cursor of records. So for those of you who are not familiar, or maybe just forgot and need a refresher, cursor is a sort of it's akin to iterable for our purposes. Here we're using Jukes cursor, and record is akin to a map of values actually, or a row in JDBC terms. Right? So in fact, yeah, that is very simple abstraction. And here we have the method to return us the size of the table by its name. We have a method to write to a table by its name and provided a list of records. And also here is a method to mask records, which means we specify which particular fields or columns we use. Actually, we use fields and columns interchangeably here. Well, we specify what particular fields we want to mask within a given record, and it returns us an already masked record. So that is. Also, we have a couple of Docker containers which will serve as input and output databases for us. These are powered by the nice test containers library, and that's all we need to know about them. And the last piece of our helpers layer is the actual masking implementation. So here I've implemented the mentioned CSS code, and we can make sure that it works with a simple test. Yes, so it converts Anton into a hobbit. That's fine. Yeah, so now we are ready to write our first flow-based piece. And let's start with just reading a table within a flow. How do we do that? So we have a holder data transfer class, which will wrap, encapsulate our further attempts in building flow-based code. And we will introduce our first flow here. So we create flows. Actually, there are numerous ways to create flows, but the most profound one is with using a so-called flow builder. It's just a flow function, unsurprisingly, which accepts a lambda with a custom receiver. So within the lambda, I should probably zoom in, right? Within the lambda, there are a couple of magic methods available to us. We will see to them in a bit. All right, so we want to actually read the data, and it's very straightforward. So now we have this cursor, how we turn it into a flow. Well, since the cursor is akin to iterable, we can do for each on it, and consuming its elements, we can further transfer them to flow, sort of we take flow elements out of this cursor, and to provide them to flow, we use this magic method called emit. And here we just use incoming record. So once again, IT is a record, and to feed it to downstream consumers, we use this emit method. And that's basically it. We've already created a flow of records. So far, so good. Let's put it to test. So the best way to test systems is with using println, of course. So yeah, by the way, how do we make sure that our records are actually being read and fed to the flow? Well, the cool thing about this lambda is any actually arbitrary code can be put in it. So for example, we can log the incoming records here, just like this. So if our flow works, we will see this log in our output. So let's check it. All right. Now let's take like one of the tables locations and try to read it. Locations. But no, what we see here is just a simple objects to string, nothing happening. And here is one important implication about flows. So once again, it's not enough to just build a flow object. So until some additional magic happens, nothing what's described here will happen. So the flow won't be materialized unless we add a missing piece on top of it. And the missing piece is a so-called collector. Let's wrap it in a separate method for now. So we write collect. And what do we have here? First of all, what does this collector actually do? The collector or collect method with Lambda, it accepts the flow's elements. It can do certain processing of them. In its simplest form, it does nothing. It just consumes flow's records, and that's it. And it is the collector that results in a flow being materialized. But one thing to notice here is that this error message, there is a complaint that the collect method can only be called within a coroutine. So once again, the flow method is just a regular method. It can be invoked from everywhere, but the collect method can only be called within a coroutine. All right, it's very simple, right? We just propagate this suspend modifier to our run method. We actually make sure that the right collect is picked by the imports. And if we try to run our data transfer, there will be this complaint again. So we'll have to make our main function suspending. And it was actually a surprise for me when I recently learned that the main in Kotlin can be suspending. But anyway, it's been around since quite early releases. Let's try it. All right.
While we are running the sample, there was a relevant question, I think, to ask.
Yep.
What happens to the database cursor? Will it close the cursor, or like, are there any interesting details we can talk about, like prefetching and all that?
Right now, we won't dive into cursor internals here, but like in its simplest form, we just consume the cursor, exhaustively, and with the last element being consumed, the cursor will out-close. That's it. So there can be more complex scenarios when we have to close cursor explicitly, but for the sake of simplicity in our example, we won't do that.
Cool stuff.
Yep.
A few folks just learned that the main can be suspended. So
yeah. A cool thing. Well, what we see in our output here is that the records of the underlying table are actually being read. So we only have 2 records here, and they both are dumped. So let's declare this a success. Now, let's add another piece to our solution, which is writing stuff. Okay, and as I described, the collector is the perfect place to add this writing. So instead of just invoking collect with nothing, we provide a lambda to it, which actually can consume records one by one. And what we do here is that we simply write stuff to the output database. And that's it. So let's check. And to be able to actually validate that it works, we can set a breakpoint and inspect our output database with all honesty, just looking at the data. So here we are. So here's our input. So yeah, we don't need public. We need actually the test database. So departments. So a couple of records in each table, and we are currently transferring locations. Here it is. And in the output, we have also 5 tables. So the structure is created by a script, but the content is being transferred by our code. So we can see that all the tables are empty except for the locations. All right. So this means that our writing works. Let's demonstrate a few bells and whistles to flows that will ease the further debugging as we dive deeper. Yeah, first of all, we can fluently add a side effecting hook for each record. So whenever a record is emitted into a flow, we can do perform a non-modifying piece of code, which can print records, which can do any sort of stuff. And here for now, let's move our writing code to the on each. We can actually chain on each invocations. Whether to do it is a matter of taste, probably, because those will be fused anyway. But let's sort of de-uglify our code and put the login into its own on each hook. Otherwise, the code is actually the same. So it should work, and we just, kind of disentangled the constructions and made them more fluent. Alrighty, now we have our end-to-end pipeline that is capable of transferring a single table at a time. And we are ready to apply masking on top of that data. So how do we do that? It is actually kind of simple, as you might have guessed. So it's just the familiar map that's defined as a extension functions for Flow. So, and it works in exactly the same way as you would expect from the collections map, for example, from the map on iterables. And here we just use, how is it called? No, not this method to transform our records. So it will be like input db. Yeah, and it needs the list of masked fields, which will propagate from a property here. So we need to modify the call side and provide the list of fields that we actually want to mask. So let's inspect the structure of the locations table. So it makes sense to maybe mask location name and address as well.
Yury, could you please increase the font a little bit so it would be more comfortable to see?
Sure. Sorry for that. Yep. Should be fine here. Oh, well now?
Yeah, it's better. Probably 18 would have been like the best. Or it's minimizing automatically. Yeah.
Yeah. Let's leave with it for now. Alrighty. Let's see how the masking modifies our output. So once again, the natural form of our data is like this. So location name is HQ or branch office, and address is Maple Leaf or Main Street. And now, yeah, it is slightly crippled, but still it looks like a location name, and still it remotely resembles the addresses. So we can conclude that our masking actually works. All right, so with just a few lines, we've got our first end-to-end pipeline working. And as trivial as it is, you can actually ask, well, how is it different from just building the same on top of iterables, on top of cursors, stuff like that. And yeah, actually right now, without any other modifications, it's pretty much the same. Maybe a bit more complex because it brings in the concept of flows. But okay, let's move on and try, for example, transferring 2 tables at once. Why not? Let's inspect our database schema again. So the simplest case would be to transfer locations and departments. Those are 2 independent tables at the root of hierarchy. So our code should be embarrassingly parallel. All right. How do I do that? So our first temptation would be to write something. Wait, is it departments? Yeah, it is departments. Something like this. And for the departments, we probably just need 1 column to be masked. All right. But will it do the trick actually? Let's see.
It seems that it will be serial, no?
I don't trust you. Let's see. Well, yeah, actually, how we can verify our assumption that it will be serial? Well, our logger is set up in a way that we see the name of the thread that currently is executing our instructions. And we can see that actually our executing thread is always main. Here it's main, 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 main. Yeah, it will be serial. Not what we want. All right, so how do we parallelize? Actually, the answer is very simple, and that's where we start touching the interaction with coroutines. We need to launch a separate coroutine per collector. Remember when I were talking about the collectors, there was that suspend modifier, and that was not by a coincidence. It actually hints that we can parallelize the execution by introducing more coroutines. So let's do that. I will explain in a bit what I'm doing here. For now, let's just launch a couple of coroutines. Not with square brackets anyway. So with this, what I'm doing is I'm like, instead of relying on whatever is inherited from the suspend fun main, I explicitly specify that I want my collecting coroutines to be run using the dispatcher's IO, which means that under the hood, our coroutines system will be using a quite wide pool of threads, which is suitable for long-running IO operations. And it has more than enough threads to deal with our 2 transfers and do them simultaneously. All right, so let's rerun our exercise and inspect the output once again.
There was an interesting question. Why didn't you pick the main dispatcher, but IO instead?
Well, first of all, in order to pick the main dispatcher, I should rely on what's sort of implicitly inherited from this context. And as I already mentioned, it's just, it took me by surprise that Kotlin even supports suspend fun main. So I'm not really sure about what's inherited from the enclosing context. So first of all, I want to be as explicit as possible because I can rely on dispatches IO, and I don't know for sure what is inherited from the implicit Kotlin magic. That's for one. Also, we could run stuff from within run blocking or with some sort of dispatches default, and especially with run blocking, which uses a single-threaded dispatcher, things can be very problematic. We can run into sorts of live logs. Is it live log or deadlock? Not sure. But anyway, such special dispatchers might not be a good fit for our purposes here. And by being explicit about what we are using for our coroutines, we can kind of save ourselves much time troubleshooting. And yeah, that's basically it.
I see.
So now, does it work? Yeah, it seemingly works. So here, I'm not sure if I can zoom in. Yes, I can zoom in. So one of our transfers is using something called dispatcher worker 3, and another one is using dispatcher worker 2, which means that our transfers are happening in parallel. So we use 2 threads simultaneously to do the actual transfer. Cool. But now that we considered the embarrassingly parallel case, what about more complex relationship? Let's try to transfer departments and projects simultaneously. And this is more sophisticated configurations because of this relationship, because of this department ID reference. Okay, will it be the same? So let's see. Once again, projects. Sorry, here it is. And for projects, let's actualize. We want to mask project name, and that's it. That will be enough. So what are your bets? Will it work?
I think it fails because of the constraints. Yeah.
Yeah, but actually, this is the matter of luck, and running it a couple of times, we will eventually run into the problem. Yes, so hopefully we are lucky. Yeah, let's call it luck. So right now it's this error. So what it says is that our foreign key constraint is violated. So let me explain what that means. So when we insert into the project table and we have a certain value in the department ID column, we must already have it ready and available in the departments table, because otherwise the data integrity would be violated, right? So that means that the entire departments table must be transferred first before we can start the transfer of the project table. And yeah, that's actually what we should implement here. And how do we do that? What kind of primitive would allow us to do that? Well, let's see. But first of all, let's think about changing the data transfer interface. So we probably need a certain notion of parent transfer somehow. And it may or may not exist. Thus we make parent nullable here. So how do we await for such a parent flow to complete before we proceed with our sort of child flow. Do we need any special primitives? Well, it turns out that we don't. What we could do is simply this. So remember, we have this collect call, which is in its simplest form, it just awaits for all the records of its respective flow to be consumed, and that's it. So if we just call the collect methods, it will be enough. It will be sufficient to kind of to use it as a signal, right? To use it as a signal that all the parent data has been written. Here we are running into a sort of type inference issue. We don't care about it. So let's just put it off the table with explicit type annotation. All right. And we need to change our call site slightly. And for that, we introduce this data transfer as a separate value. Here we just use, sorry, it's just run. And we feed this parent to our child transfer. That should do it. All right, let's try. Oh no.
Drum roll.
Drum roll, yeah. But this time the problem is different. Why so? So right now, duplicate key violates unique constraint. What does this mean? Well, it appears, well, I don't know actually. Let's troubleshoot it. How do we do that? All right, we can add some other hooks to our code that would show when our transfers are started and when they are finished. And let's see what's going on with our transfers. All right, I'll zoom in. See this? Yeah. So we have our departments table being transferred twice. Why so? Well, to understand that, we need to introduce the concept of cold flows. And cold flows are what's being created by such the flow builder by default without any additional means. And cold flows are special in a way that whenever we collect them, the entire body of the flow builder gets re-evaluated. And so do all these hooks, and so does our writing hook. So we, in fact, collect the department's flow twice. And how so? Well, let's see. Once we do that in this explicit run, see this collect, right? Cool. And another one comes from this line when we do collect the parent, so in the child flow, right? So right now the fix is very straightforward. Since our cold flow for the parent is activated by the child flow being run, we can simply remove the explicit collection of the parent flow, and that will do the trick. Yeah. So once again, what's happening here? When we invoke this run, we start collecting the child flow. But before we actually tend to the child flow elements, we first collect the parent data flow if it's present. So in fact, with one shot, we got 2 flows collected. That's it. Okay. Now we are ready to elaborate our example even further and add the transfer of the second child table, employees. And we'll see whether it will look exactly the same. It will be employees. Does work. And here we will be masking a whole lot of fields here. Sorry. Let's remove coroutine name for now. First name, last name, and email as well. All right. So will it work this time? Not sure. Let's see. It works, surprisingly. That's because we don't specify parents here. And once we do, once again, what are our chances to get away? No. And if we inspect our output once again, well, it's still the same problem. Once we start another child table transfer, we run into the same problem once again. And this time we won't get away with just removing one run. So let me reiterate that. Once we collect one child table, we activate the writing of the departments, and the second time when we collect the other child table, the departments gets transferred once again. And we are not doing any absurds. That's why we try to overwrite data in the departments and fail. All right, so now let's think how we can fix that. And that's where we need another abstraction that is called hot flows. So what is hot flow actually? Let's unroll this abstraction gradually. For now, let's just write some sketchy code and see where it gets us. So we somehow need to be able to deduplicate the departments tables transfer. And for that, we need to convert our cold flow for departments into a hot flow, which would cache actually our records and result in the data being transferred and being written only once. So for now, let's just write the sketch. It will be a sort of hot flag, and depending on that, we will need to transform our flow somehow. We don't know how yet, but let's write it in this way now. And if it's not hot, we just leave it at this. How do we do that, actually? Well, if we have a cold flow, we can transform it into a hot flow with just one method invocation, which is shareIn. Let's try it. But first of all, okay, good enough for now. This shareIn method accepts a coroutine scope. Okay, let's write it for now.
Could you zoom in again, please?
So eventually I will zoom in each and every file, and the problem will be solved. Something called shareIn started. Don't know what that means yet. And that should be it. Let's just propagate our scope for what it's worth here. Again, we don't overthink it for now. We just pass it because it's required by the method signature. And actually, we don't need this flag anymore because the presence or absence of the scope property itself will be a good enough signal for us. So if it is provided, we convert the flow into a hot one. If it's not, we'll just leave the code flow as it is. And the only case where we need our flow to be converted into a hot one is the transfer of the departments table. Okay. So why can we write scope equals this? Is within this lambda, our custom receiver is actually the coroutine scope, which we can see from the signature, right? So we just write this, which will refer to the enclosing coroutine scope. Okay, and a few words about shareIn started lazily. Well, not now, in a few minutes. Let's try it first.
There was actually a good question or a general comment about the whole approach. Is that wouldn't it be just easier to drop all the constraints from the destination tables and pump the data and then re-add the constraints?
Yeah. So the answer is, as usual, it depends. So for very large and complex databases, depending on the underlying RDBMS, it may or may not be a cheap operation to just disable constraints. We cannot actually drop the constraints, right? Because one of our overarching goals is to preserve the topology. Without the constraints in place, our output database does not hold the full resemblance to the input one anymore. And it's very often that we do want it. So for example, testing application against a database with non-existent foreign keys can produce strikingly different results than testing against a fully blown database with all constraints in place. But there is a workaround for that. During our transfer, we could temporarily disable the constraints checks and just insert stuff there, relying on our our code to do the things right and re-enable the constraints once the transfer is finished. We could do that depending on RDBMS. Again, it will be dependent on whether we are using Postgres or MySQL or any other engine. I can speculate that sometimes it's not even possible. Other times, it will be very time-consuming just to disable the constraints on the output database if the structure is complex and we have like thousands of tables, sorry. And also, when we re-enable the constraints with data already pumped into the output, there can also be issues because all the constraints will need to be revalidated so that the final state of the database will be consistent. And this can also be a very time-consuming operations. So yeah, depending on the context, sometimes it's possible, but other times it's better not to disable constraints, and even better than like dropping them altogether, but like pay more attention to the topology of the database in the transfer code. Yeah, hopefully this answers the question.
I hope to.
Yeah. And while we spoke, the things successfully finished, and now we only have one transfer for departments, so the issue is addressed. But well, it's totally unclear what's going on, right? What have we done? Let's try to unroll it. First of all, what does it what does it even mean in the first place? ShareIn, what does it, well, what is it? In order to unveil this mystery, let's add a couple of tricks. First of all, since we have a scope, this somehow implies that coroutines are involved under the hood, right? So let's try to extend our scope with a custom coroutine name that will be easily detectable in the debug mode, so we can see what that coroutine actually does if it exists. And also here, let's give our explicit coroutines some names as well. Okay. Projects. And let's stop at the breakpoint and see how it looks internally in terms of coroutines. Does it give any additional information to us? Okay. Yeah, first of all, one thing to notice before we can jump anywhere is that our program does not terminate anymore. What a surprise. Well, the thing is that hot flows are non-terminating by definition. So when we had a cold flow, our flow was sort of run to completion in a bounded amount of time. And well, after reading as many records as there are in input databases, we just terminate it. But that's not the case with hot flows. This is the documented fact. And for now, let's take it for granted. But how do we turn our non-terminating flow into a terminating one? The answer is simple. We put an upper bound on the amount of elements being transferred. We do this with the familiar take method. And here we use the size of the table as the limit. So now we should be good to go. So we only take a couple of records from the underlying flow, and then it must go. Actually, there is an issue with breakpoints. For some reason, the program does not stop at them. So I typically do the following. Maybe some of you know what's going on, but I haven't found a cure for that. So I'll just add a construction here, which is not needed at all, because this join all actually does not add any value. We are already within the coroutine scope, so the coroutine scope is finished when all the child coroutines are finished, but it's more convenient to set a breakpoint here, and hopefully this will get us somewhere. All right. So now that we are waiting on a breakpoint, what do we have in terms of coroutines? So here in the debugging mode, you can inspect the coroutine state. And here we have a sort of empty dispatcher, and that is what we got from the Kotlin magic through this suspend fun main. And stuff within dispatchers IO is ours, our very own stuff. So what do we have here? 3 coroutines. Can I zoom in again? No, I can't. Sorry. Projects. This one. Employees. Another explicit coroutine. And departments shared. You see? Once again, this is our custom coroutine name. So, in fact, our hot flow is nothing more than a coroutine under the hood. So whenever we create a hot flow, there is a separate coroutine being run beneath the things for us, which is responsible for consuming the original code flow and sharing its elements downstream. So the hot flow can be tuned in a number of ways, which we won't touch on here, but just a few words. This sharing actually starts to make sense now. Actually, this is when our coroutine starts emitting elements downstream. Here we are using lazily, which means that our hot flow coroutine will wait until the first subscriber arrives, and then it starts kind of feeding elements downstream. We could also specify eagerly, which would mean that the data transfer in the hot flow would start immediately after we kind of converted, after we created it, after we converted our cold flow into the hot flow. And that would mean that even the first subscriber actually would be, it would be possible for it to lose some data, just because the coroutine does its transfer independently of any subscribers being present or absent. But for now, lazily will do for us. And actually, you can specify more complex strategies how to deal with sharing. We won't touch on them here. It's a completely different topic. Sharing lazily works fine for us. Cool. Also, we can double check that our coroutines are what they are, or at least what we expect them to be. We do that by inspecting the coroutine creation stack trace. So, for example, our project's coroutine, is it really our explicit coroutine or not? Let's see. Well, it's claimed to be to be launched in app KT line 10. Here it is, right? And the hot flow coroutine. Once again, to the coroutine creation stack trace. Data transfer line 38. Here we are. Yeah. So hopefully this all is clear now. So by this magic, we just run a separate coroutine, which does the dirty work for us and all the heavy lifting. And now we are ready to move further. So right now, what we could do is to actually run the entire clumps of tables being transferred. So let's add employee projects. And that's where things could get interesting. Approach, all right. So fortunately, we have nothing to mask here. Let me expand a bit. So we just use empty list for the list of masked tables, masked fields, sorry. Okay. But what should be the parent of this transfer? Once again, let's take a look at the schema. Well, it turns out that there are multiple parents this time, and our interface is just not prepared for that. So let's modify it a bit. So now we can have a list of data transfers, which defaults to no parents at all. But now the problem is, how do we await for all the parents to complete, right? So equipped with the knowledge, you might be tempted to write something like this. So like data collect. All right, is it good? Well, it turns out that in this case, we would collect our parents sequentially, so our throughput will be limited. imagine we have, it's a contrived example, but still, imagine we have 100 parents. With this construction, we would be collecting them one after another, after another, after another. And that's not what we want here. We want to utilize concurrency, right? So how do we do that? All right, we do that with a brand new operation, which I have a nice shortcut for. Let me explain what's written here. And I'm talking about this new piece. All right, so if we don't have any parents at all, this is identical to having no parents at all. So we just skip over this entire piece. But if we do, we use the new operation called flatten merge. So first of all, we convert our parents to a flow. And we do that in order to end up with this data type, flow of flows. And with flow of flows, we enable ourselves with another class of operations, flattening operations, one of which I'm using here. So flatten merge, first of all, it requires an opt-in. What it does, it takes all the flows in the kind of parent structure and collects them concurrently, spawning as much as concurrency coroutines at the same time. So here, for example, if we have two parents, there will be up to 2 coroutines launched in order to collect our parents. So this is greatly increases our throughput right now because all the parents will be collected in parallel. Actually, we could written it in a different way, such as flat map merge. Yeah, but that's not so fluent, and actually its usage is sort of maybe discouraged in the official documentation. And to me, too, the combination of map and flatten merge is just clearer. All right, and now we're fully equipped to do the transfer with all the parents in place. So right now we just need to modify our call sites. Parents. Here to list. So we have projects. Where is it? So here we are. Quite ugly so far. Actually, the funny thing about this construction is that we don't need all these separate runs anymore. So we can just remove them. So we all have just these definitions of data transfers, which are activated with a single run. And it's much cleaner now. And why so? Again, it's because our run will collect the data, which will activate the collection of parents, which in turn will activate the collection of its parent and up the hierarchy. So with just one simple call, we collect our entire flow system. Cool. So here we are. We were able to transfer this entire grouping of tables. We won't bother ourselves with the location because it's trivial right now. Another interesting thing to touch on is how do we extend our flows to support some custom operations, for example. And here, one thing to notice is we currently write one record at a time, all right? Which can be not very efficient. We might want to write our records in batches. It's reasonable. Why not? So, unfortunately, unlike collections or iterables, our flow interface misses the chunked method, which we have to add ourselves. Let's do that. We don't even need flow extensions object. All right, how do we do that? With extension methods, of course. It's like chunked chunk size, which will return. Right, where should I put t? Here. Right. And the nice thing that we don't need any more knowledge to implement that ourselves. How do we do that? Straightforward. Mutable list as an accumulator. Then we declare our flow. Again, the familiar flow builder. The type inference does all the work for us. We don't need these type variables anymore. And what do we do here? So within that flow, we start collecting our original flow. And as more records come in, we just add them into the accumulator. Cool. If the accumulator overflows, we'll just emit it downstream. As simple as that. We clear it to start accumulating another chunk.
Could you zoom in again, please?
I must have expected that. Yep. Yeah, and if the original flow has size that is not multiple of the chunk size, we could end up with a partially filled accumulator. So here we'll just need emit once again if the accumulator is not empty. And that basically concludes our extension. So again, we don't need to know anything else beyond what we already learned. Just a couple of invocations and we are ready. All right. And we can replace our data transfer as it is. So here we put chunked and let's pick some chunk size. What's your favorite chunk size? Mine is 2. Okay. Now we have our signature changed. We can actually move this before the chunked so that we don't have to update them. And here our data got the new type notation. However, the most complex part now is this. We'll just need to think about the flow, not in terms of separate records, but in terms of chunks. So we need to make adjustment here. Fortunately, I've already prepared the formula for you. We don't need to think about it. It will be rounding up. And that's it. Unless we miss something and it won't compile. Yeah. So in fact, with just a few strokes, we added the ability to work with chunks to our code. And that's another blessing in disguise about flows, right? You don't need to learn any new concepts. It's just as simple as defining new extension methods, and that's basically it. All right. So Here it is. Here is our complete example. One disclaimer about it, though. Uh, Especially inquisitive watchers could notice that actually what's going on here is not really so different from using the thread pool executor underneath. Why? Because our data transfer here uh, actually emits in a tight loop without yielding the underlying thread. So in effect, we will tie up the underlying threads for the entire lifetime of the respective cursor. And unfortunately, this is inevitable if we use synchronous I/O. If we used, for example, like asynchronous facilities to interact with databases, things could be different. Or we could maybe yield underlying thread if we need to. I doubt that it will provide any performance benefits here. Actually, I think it's vice versa. It will be unnecessary overhead here. But this combination of synchronous I/O and asynchronous building blocks, unfortunately, has its shortcomings. And yeah, I just mentioned this as a disclaimer. And otherwise, we are good. This concludes our example.
Nice. You kind of touched a little bit on this performance issue with concluding the about the blocking interaction and so on.
Yeah,
And in your final solution, when you decided to apply Kotlin flows in your product, what was the change? What was the like great benefit? Uh, did the program start working faster, or what was the final outcome?
yeah. So first of all, it apparently became much, much faster. And that is actually to give you some numbers. So the original prototype was sequential, so well, requirements about its performance are quite relaxed. But it was maybe, I don't know, a few megabytes per minutes, something like that. And with the flows, we were able to squeeze as much as tens of gigabytes in minutes from the entire system, and that is quite good, provided the fact that we, besides like this simple transfer, we have to do some very complex and CPU intensive things such as masking, like here, or generation. But again, that was the growth from megabytes to tens of gigabytes. And also, one more maybe profound and valuable thing about structuring our programs with the help of flows is that it became so much easier to reason about the programs. And whenever we add new tables, new relationships to our databases, they are just automatically picked up, and we don't care about how they are managed in terms of thread pools. We don't need to submit anything anywhere. Once we structure our program around this line of reasoning, when we think about our program as a sort of hierarchy of flows, things start unfolding automatically. That's just it. Uh, the kind of, we just define the structure, we run execution on top of it, and the rest is being dealt with by the underlying flow machinery. So the productivity increase, I believe, is even more drastic.
Nice. Well, we are severely over time this time, but the topic was so interesting and you covered it in depth, and it was amazing to see how like simply you could do complex things. And folks do have some other comments and questions, but I guess we can take them offline into the comments to the video because this will be published. The session is recorded. If you have any questions, just type in the comments and we will address them later. The code for the presentation, I guess Yury can put on GitHub if it's not there yet, maybe, and share with the public so that the folks can learn and play with it.
Yeah.
Otherwise, you will have to recreate everything by the video. Uh, Anyways, I really enjoyed the session, and thank you everybody for coming to our stream and engaging with the comments and questions. And thank you, Yuri, again for taking time to prepare all this content for us.
Yeah. Thank you very much. Been a pleasure.
Thank you, and everybody have a nice Kotlin.